and then again a for loop which we are running 200 times. As we can see, the condition is less than 200, and what we are displaying at port B, that is the invert of port B, so which means that when the first time 0xAA would be displayed, and then the invert of the port 0xAA, which means 0x55, which means 10101010, that will be displayed. Then again this will be inverted to 0xAA, and then again to 0x55, and this way it will toggle 200 times. Now in example 4, we are writing an Avr C program to send values of -4 to +4 to port B. So again we have included an input output header file int main, and then in the int main we are again creating a character array in which we are placing all these values from -4 to 4. So -4, -3, -2, -1, 0, 1, 2, 3, 4. Again unsigned character Z for the for loop, and setting the port B output direction, and then in the for loop we are displaying the each of these characters and the port B, and again these all these values that will be displayed would be the ASCII hex values of these characters. It won't display -4, -3, -2 or all these values in binary on port B, but instead of it will be displaying the ASCII hex values in binary at port B, basically ASCII binary values on port B. Then in example 5, we have C program to toggle all bits of port B 50,000 times. So in this again inside integer Z, so we have created an integer Z, and then set the port B direction to output, and then created a for loop for 50, which will be having a condition Z less than 50,000 because we want to run it 50,000 times. And then on port B we are displaying 0x55, which is basically 10101010, and then we are displaying port B equal to 0xA, which is 01010, so basically all the pins are being toggled, and this will continue to happen 50,000 times because of our loop condition. And now moving towards example 6, we will be toggling all bits of port B 100,000, so basically everything will be same in the code, or the only change will be that we will be changing the unsigned integer, moving from unsigned, replacing the unsigned integer Z to unsigned long Z, because integer has a limit of we can see here that unsigned integer goes from 0 to 65,535, so it cannot go to 100,000. So for that we need to use long, which goes from 0 to 429, 4967, 295. So that's why it can accommodate 100,000 in its range, and we can use that to toggle 100,000 times. Now we are toggling all bits of port B continuously with a 100 millisecond delay. Assume that the system is at mega with 16 megahertz oscillator. So in this we will be creating, first of all let's look in the int main what is happening. So set port B to output, and then we created a while loop which will continue for ever, so till the program is running. And in port B we are displaying AA, which means 0101010, and then we are calling a delay function which is named delay 100 milliseconds. And here we can, when we move to this 100 delay millisecond function, and this is a void function with parameter, no input parameter, and what we are doing is volatile unsigned long I, and we have created an unsigned long variable I, and this I is started from 0, and we get a for loop to run it 47060 times, which means it will just basically the loop will be executed when this function will, because this loop will be executed for 47060 times. It will just do nothing, so basically it will just waste some time, computation time, because time will be taken to run this whole loop, so that all this computation time will be wasted. And this 4760, so 7060 is not just a random number, so but it has been calculated for 100 millisecond, and by using with the help of the 16 megahertz frequency. So for that we have, after all the calculation of the time period and how much time it takes for one for loop cycle, so we have for this function to perform, uh, so we have calculated and we have concluded that we need to run this loop for 7060 times to waste 100 to waste 100 millisecond, to create 100 millisecond delay. And on board we will display this 0x55, which will basically toggle all the pins, and then again a delay of 100 millisecond, and this will keep continuing happening. Then moving to example 8, we are toggling all pins of port C continuously with a 10 millisecond delay to the predefined delay function. So now we are using a predefined delay function. So to using a to the predefined delay function, first of all we have to define the clock cycle or the oscillator frequencies, crystal frequency for the particular for a particular microcontroller. So for that we will write hashtag define fcpu, and then write what the frequency of our crystal oscillator. So here we have 16 megahertz frequency of crystal oscillator, so we will use 16,000, and then we will write ul. After that we will include the delay library, delay header file. So for that hashtag include util/delay.h, and then all the other things, input output header file and int main will remain same. And now in the int main we'll be setting all the port B to output direction, and then create a loop while one. So port B is setting up, so we have created a while loop which will continue till the program runs. So the port B will be displaying FF, which means all the pins will be high, and then we'll call this function which is in this delay header file, delay underscore millisecond, and then in parameters, input parameters, will parenthesis will put the parameter which is 10, so this will give us a 10 millisecond delay. Then we will toggle again, toggle the output to 0x55, and then we'll again give a delay of 10 millisecond. Now in example 9 we are LEDs are connected to pins of port B, and we are writing an AVRC program to show the count from 0 to x 0 to ff, which is 25 in decimal on LEDs. So again including all the necessary delay header file and input output file and int main, and writing the crystal oscillator frequency. And then first thing we are doing is setting the P port as the output direction, and then creating a while loop in which we are just simply incrementing incrementing by 1 what the current value of port B is. So basically at the start port B has a value 0, so port will be 0 plus 1, so it will display 1, and then we have a delay of 500 millisecond. Again now port B will be having 1 plus 1, so 2, and then similarly 3, 4, 5, 6, and this will be continue be displayed after a delay of 500 milliseconds, which is 0.5 second. After this we are at example 10, which is a C program to get a byte of data from port B and then send it to port C. So input output header file int main, and after that we are creating an unsigned character temp, and then setting the port B direction all pins to input, and then setting all the pins of port C as output direction. Now we have created a while loop, and here we are giving the temporary variable the value pin B, which will be basically where we will be giving input, and ports at port C, which means we will be displaying at port C the value stored in temp, which will be basically the input at pin B, port B. So c equals to pin b here, but it is a safe practice to create a temporary variable and store the values in it. Then example 7, we are writing an AVRC program to get a byte of data from port C, and if it is less than 100 we send it to port B, otherwise we send it to port D. So here first of all we are setting the port C to input all the pins to input direction, setting all the pins of port B to output direction, and setting all the pins of port D to output direction too. Then creating a temporary variable unsigned character, and then again a while loop in which we are storing the input at port C in the temporary variable, and if we are giving condition temp is less than 100, we will be displaying the value stored in temp, which is basically the input at port C. We will be displaying it to out at port B, else we will be displaying it to port D. In example 12, we are basically in example 12 we have to run this program and examine the results. So first of all we can see here we have set it the direction of port B as output, port C as output, port D as output 2. So in first we have port B. At port B we are giving the output 0x35 hexadecimal and 0x0f. So here an AND operation is done being between these two hex values. So what will be happening here is 0x35 in binary will be 0 0 0 1 1 and 0 1 0 1, and when this will an AND operation will be performed with 0f, which is 0 0 0 1 1 1 1. So we will see that in AND we know that AND gives 1 when both the inputs are 1. So basically because this 0x0f has all first four bits 1, so which means that port AND operation of this will give us 0x05, because 3 AND with 0 will give us 0, and 5 AND with f, which is all 1, will give us 5. Similarly an OR operation is being performed here, and then a bitwise D operation, and then at port B we are displaying this inversion of 55, which will be 0xAA. Now in example 13 we are writing a C program to toggle only 4 bit of port B continuously without disturbing the rest of the pins of port B. So we are basically toggling only one pin. We have to just continuously change one bit of port B, and we do not need to change any other ports of port B pin port B. So first of all we are setting port B at the output direction, and then created a loop in which first we are doing port B equals to port B or 0B binary 0 0 0 1 0 0 0 0. So when anything is odd with 1, here we can see if anything is odd with a 1 results in a 1, anything odd with a 0 results in no change. So here we can see port B or this binary value, so which means that whatever value the port B has, it will only change the first, second, third, fourth, the fifth bit value to 1. All others are odd with zeros, which means all of them will be remain same. Only the fifth bit, no matter whatever the value it had on port B, it will be just changed to 1, and all others will remain same. The next time we are doing port B and 1 1 1 0 1 1 1 1 1. So when anything is ended with 1 results in no change, anything ended with 0 results in 0. So as we can see, we have AND all the bits except the fifth bit with 1. So none of those bits will change, only the fifth one is only the fifth one is ended with 0, so which means it will change to 0. So basically we are changing only the fifth bit from 1 to 0 in this whole program without altering any other bits. Now example 14, we have to monitor bit 5 of port C. If it is high, we have to send 0x55 to port B, otherwise 0x8AA to port B. So again, declaring port B as output direction, port C as input, and port D as output. And if pin C and 001 00000, so we know when anything is ended with 1, so it remains same and others become 0, so which means that the condition is that if pin C's first, second, third, fourth, fifth, sixth bit is 1, or sixth bit is not equals to 0, port B will display 0x55, else it will display 0x88. So which means if pin C's sixth bit is high, it will be the condition will be true, as it will not be equals to 0, and 55 will be displayed, else 0xAA will be displayed. In example 15, a door sensor is connected to a bit 1 of port B and an LED connected to bit 7 of port C. And we are going to monitor the door sensor, and when it opens, turn on LED. First of all, we have set DDRB and 0B 1. So again, we know if anything is ended with 1, there's no change, and anything ended with 0 will be changed to 0, which means that only second bit of port B is declared as input, and in DDRC or 100000, and or we know the bit which is 1 results in 1, and when there is anything ORed with 0 has no change, means that only the 7th here the 8th bit of port C will be set 1, which will be set as output direction, and all others will have no change. So here we have a condition pin B and 0, which means that if the second bit of pin B is high, so this if condition will true, and port C's 8th bit will be high and it will turn on LED, else what will happen is we will clear pin 7, and which means that at pin 7 we'll be having 0, and all other bits of port C will be remain unchanged. Now in example 16, the data pins of an LCD are connected to port B. The information lands from the LCD whenever its enable pin goes from high to low. It is connected to pin 5 port C 6 pin. Write a C program. The Earth is but one country in this LCD. So here we have to display this message on a LCD. So first of all, we have created a character array called message, and here we have written the Earth is but one country, then a unsigned character Z. Then we have set the port B to the output direction, and DDRC is odd with 001 0000, which means that only the fifth pin of the port C has been set as output. And then we have created a for loop which will run 20 times, because character array length is 28, we know that. And one by one at port B each character by character message would be displayed. And on port C we can see that it is odd with 6th bit high. So this means that 6th bit will become high, which means it will turn on, which will become 1, and all the others will be remain unchanged. And then port C end with 110 11111. So this means that uh, ports port C's 6th bit will remain will become 0, and all others will be remain unchanged. So now moving on to example 17. Here we will be reading pins 1 and 0 of port B, and if these pins has the combination 0 0, will be showing 0 at port D, ASCII binary value of 0 character at port D. Similarly, if the combination is 0 1, will be sending a character 1, and then if 1 0, then character 2, and then 1 1 character 3. So here we are sending port B as input direction, port D as output direction. Then in the while loop we have a unsigned character Z, which is storing the input from pin port B, and we are masking all the other bits except the first and the second bit. As you know, AND function keeps the first and second bit when the anything is ended, so with 1, so the bits remain have no change, and when ended with 0, they change to 0. So when C is ended with 0 0 0 0 0 1 1, so the first and the second bit will remain unchanged, and all the others will be changed to 0. Then we have used a switch case where we have given Z past the case of switch Z as a switch condition, and if it is 0, so we will be displaying a 0 character ASCII binary at port D, and if case is 1, then 1, and then 2, then 2, then 3 is show character 3. In example 18, we are monitoring bit 7 of port B. If it is 1, make it 4 bit of port B input, otherwise change pin 4 of port B to output. So here the DDRB direction is being set by using the ended, so we know that with ended with 0 gives 0, and ended with 1 returns in no change. So this means the 7th bit will become 0, and it will be DDRB 7th bit will be set as output input direction. The while loop, and in the while loop we have a condition if that pin B and 1 0 0 0 0 0, which means that if you know AND operation is when AND operation is when with 1 there will be no change, and with 0 all the others will be 0. So whatever will be at the last, which means the 7th bit of port B, that will remain unchanged, or it will when it will be high. Basically, when the 7th bit which we have set as the to input direction, when it is 1, the if condition will be true, and the output port B's 4th pin, as we can see, it is ended, and it is 0, 4th pin, which means the 5th bit. So it is 0, which means that the port B's 5th bit will be set to input direction. Else the we have to do the OR operation to make the 4th bit as output, because when anything is odd with 1 results in 1, and with 0 it will result in no change. So we can see at the 5th bit 5th bit there is 1, so which means that 5th bit will come as output direction, others will remain unchanged. In example 19, we have write a program to get the state of the bit 5th of port B and send it to bit 7 of port C continuously. So again, here we have set the fifth port, we can see, because it is and fifth bit is 0, so basically fifth bit will remain 0 and all the others will remain unchanged. So DDRB is fifth bit is sixth bit is input direction set, and in the C we can see odd operation, and the last seventh bit is 1, which means that the last eighth bit will be 1, which will be set as output direction, and others will be uh, no change. Then we have the while loop. Here in while loop we are setting the if condition, that if pin B and 0 0 1 0 0, which means that if the sixth bit is high, then the if condition will be true. So if the sixth bit of pin B is high, then port C seventh bit will be set to 1, which will mean it will be yes, if there is an LED or anything, we will be sending high at seventh pin of port C, else it will be sending 0 to the port C's eighth bit, last bit. Then in example 20, we are toggling all the pins of port B continuously, first using the invert operator and then the XOR operator. So for XOR we know that so first of all let's look at the invert sign one. So here first of all we are setting port B output direction, port B, then we're displaying the 1 0 1 0 1 0 1 0 1 0 at port B, and then while loop, and then again we have seen this code previously. We are using the invert operator to toggle the port B. Then the XOR operator. So now we will do the same thing with using the XOR operator. So here we can see the changes in the while loop. So in the while loop we will be using port B XOR 0xFF. Whenever, so we know that whenever anything is XORed with 1, it will complement it, which means inverted, and if it is XORed with 0, it will remain. As we can see here, 0, there will be no change, so it will remain same. So when we using XOR with 0xFF, is all the bits are 1, so which means that all the bits will be complemented. Now example 21, we are using bitwise assignment operators. So we will rewrite example 7-18. So using the bitwise compound of assignment operator. So here instead of equals to like if here we can see DDRB and equals to 0B 1 1 0 1 1 1 1 1 1. So here instead of writing DDRB equals to DDRB and 0B 1 1 0 1 1 1 1 to set the fifth sixth bit to input direction, we can simply replace it with and equals to and write it like this. Similarly, all the code is same to the example 18. The only difference that wherever we are performing an OR operation or AND operation, we are using the AND equals to or OR equals to operator. Similarly, in this one here also we have done the same thing. Moving on to example 20. So here in this example we'll be using greater than and lesser than signs to set directions of different pins. So first we have position D7 and we have to change it to 1. So we write 1 lesser than 7. Then to change position D2 to 1, 1 lesser than 2, to change position 4 to 1, 1 lesser than 4, and to change position 5 to 0. So here we will again write 1 lesser than 5. With this will change the fifth position to 1, and then we are using the invert operator, so which means it will do the opposite of it, so which means it will set the fifth position to, instead of 1 it will set it to 0. Similarly for position 3 and position 1. Example 23. Here we monitor 7 bit of 4b. If it is 1, make it 4 bit of 4b. So for the input, change port pin, if not, change pin 4 of port B to output. So first of all, here in the int main we are performing the AND operation and setting the the 7th of bit of port B to inversion of 1, so which means to 0, so which means DDRB 7th bit will be set to 0, so which means as input. And in the while loop we have an if condition with and if pin B and 7th position is 1, which means if 7th position is 1, then if condition will be true, else in which we have written DDRB equals to DDRB and invert of 4th position to 1, which means that that it will set the port B's 4th position to the direction input, which is 0, and else if this condition is not true, then it will set it at output. Now example 24. Here we will be writing C program to get the status of bit 5 of port B and send it to bit 7 of port C continuously. So here again we can see that invert operator with at 5th position from 1 to 0, so which means 0 will be which means DDRB's port B's 5th position will be set to 0, which means as input, and DDRC's 7th position will be set to 1, so it will be set as output direction. And again the while loop, in which we are giving the condition if pin B and 5th position is 1, which means if the 5th position of pin B is 1, then a if condition will be true and port C's 7th bit will be set to 1, else port C's 7th bit will be set to not 1, which is 0, so which will be set to 0. Now example 25. Again that we have the same door sensor example we did above, but this time again we'll be using those lesser than operators and compound assignment operators. So first we have this here we have defined LED as 7 and defined sensor at 1. So first line DDRB and equals to not 1, which means that not 1 less than 1, which means first bit not 1 set as not 1, which is set as 0, which means DDRB's first bit is set as output as input direction, and then DDRC not or equals to 1 LED, which means LED is 7, so which means the 7th bit will be set to 1 of port C, which means it will be set to output direction. And the while loop, again we have the if condition. If pin B and the first bit is 1, then if condition will be true. It means that port B's first bit, if it is 1 high, then if condition is true and LED which is on, which means that the 7th bit of port C will become high, else the 7th bit of port C will become low, which means the LED will not be on. Now on example 726, we have a C program to convert PEG PCD 0x29 to ASCII and display the bytes on port B and C. So first we have an unsigned character X and then Y, and side character my byte, which has a value of 0x29, which is the BCD value, which will be back BCD value, which will be converting to ASCII and display on port B and C. So first of all, setting the port B and C to output direction here, and then x equals to my byte and 0x0f, which means that my byte has value 2 hexadecimal value 29, and we are making have ended it with 0x0f, which is 0001111. So which means that all first 4 bits will remain same, they will be unchanged, and other last 4 bits will be changed to 0, and this value will be stored in this variable unsigned character x. Then we are displaying it. We are displaying that ASCII value on port B. So for that, port B equals to x OR with 0x30, which means that with OR we know that when it is ORed with 0, so there it remains unchanged. So which means that x, which has a value of 0x09, will be ORed with 0x30. So this will give us basically 0x39, which is the ASCII value for 9. And then y, we have y, and y equals to my bit and 0xf0, which means that the last 4 bits are 1 and first 4 are 0. So y will have the value 0x20, and then we are using this we will shift these shifts operators. So we will shift these 4 bits to the first 4 bits, which means the lower 4 bits. So and then display it on port C, and again ORed y ORed with 0x30. So basically at port C will be having displayed 0x32, so which is again ASCII for 2, ASCII hex for 2. So this way port B will be displaying 9 and port C will be displaying 2, and both of these will be the ASCII binary codes of these two characters. Moving on to example 27, writing an Avr C program to convert ASCII digits 4 and 7 to PEG BCD and displays them on port B. So first of all, we have a character BCD byte, and then a character W, which has a value 4, and a character Z, which has a value 7. Then our port B has set to output direction all pins, and then W equals to W and 0x0f, which means all the that means that the first 4 bits are set to 1 and will remain unchanged, and all others are set to 0. So W has a character 4, which means it has a ASCII hexadecimal value of 0x34, and as we do W equals to W and 0x0f, so which means 0x34 and 0x0f. So this will result in 0x04, because the last 4 bits are, or the first 4 bits, the least significant bits are 1, so it will only make the least significant 4 bits of W unchanged, and all the other bits will be changed to 0. So W will be changed to 0x04, and then we will shift all these values to 4 spaces left, and this will make the most 4 come at the most significant bits, 4 most significant bits, and then we are doing the similar thing with Z, and then BCD byte is equals to W or Z. So which means that W, which has a value of 4, and Z has a value of 7. The 7 is value 7 is at the least significant bits, least 4 significant bits, and 4 is at the most significant bits. So when these will be odd, we will be having 4 7 at the port in the BCD byte variable, which will be displayed at port B. Example 28, here we'll be looking at we're finding the checksum byte, perform the checksum operation of integrity to ensure data integrity, and if the second byte 62H has been changed to 22H, show how checksum detects the error. So first here, for the checksum, we'll simply add all these 4 1 2 3 4 data that we have. We added all of them, so we have get 118H, and we'll drop the carry of 1, and then we'll take the second complement. So for that, after taking the second complement, we get this E8H, and to check the data integrity, we'll just simply add the second complement to all these 4 hexadecimal data, and if we get the 00 hexadecimal value, that means that our checksum is data is ensured and checksum is successful. There is no error. And for the last C part, we have changed 62H data to 22H and performed all these steps again. We can see that in the result we do not have 00 hexadecimal, we have C0 as 0xC0, so which means it is not equal to, so which means that the data has an error, and an error which has been detected. Now example 29, we are given a program to calculate a checksum byte for the data given in example 28. So we will now create a code for this. So we have created a character array of my data, which has all the 4 data. Then we have created a sum character, then a character X, and a character checksum byte. First of all, setting port D to output direction, port B to output direction, port C to output direction. Then we have created a for loop, and we are running it 4 times because we have 4 data. So first of all, at port D we will be displaying the data as it will be being added. Then we'll add in the sum, we will be adding this data one by one, and then we'll be displaying at port B whatever our sum is. After this process of the sum total has been done and all of that has been displayed, then we will take the complement of this sum and then add 1 in it to get basically the 2's complement, which is what this is the simple method for 2's complement, performing that. And then we'll display the port C, the result of this at port C. So if port C will be displaying 00, will be know that our checksum is correct, which means if no light is or no high is given at port C, we'll know that the data is ensured, and if not, we have a high at any pin of port C, we will know that the data has errors. Example 30, we are writing a C program from step of 20. If the data is good, send ASCII character G to port D, otherwise send B to port D. So we are again performing that checksum code again. The only difference here we have that if the checksum, we have given the condition that if the checksum equals to 0, so which means that if after adding 2's complement and adding all with that data, if we get 0, then our port D will display G of ASCII binary value of G character, else it will display B at the port D ASCII binary value of B character. Example 31, we are writing a C program to convert 1111101 to decimal and display the digits on port B, C and D. So as we know, this value is FD, which is in decimal 253. So we have these unsigned characters X, bin byte, D1, D2 and D3. So first of all, we have set all the ports B, C and D to output direction. Then bin byte equals to 0xFD, which is 253, which is we have set as the. Then X equals to bin byte divided by 10. This is done to separate the. In this we will be dividing our bin byte, which is 0xFD by 10. So as we know, 253 is our bin byte, so if we divide it by 10 we will get 25. And then in D1 we are saving the remainder bin byte divided with modulus 10, so which means we will be saving 3 in D1. X will be having a value 25, D1 will be having value 3. Then D2 is x modulus 10. So D2 is x mod, so which means 25 modulus 10. So this will give us 5. Now D2 has a value 5, and then D3 will be x divided by 10. So 25 divided by 10 will give us 2. So D3 will have 2. So basically D1 will have 3, D2 will have 5, and D3 will have 2. And which are the three digits of the number 253, and all of these will be displayed on port B, C and D separately. Example 32 is C program to send out the value 44 hexadecimal serially 1 bit at a time via port C pin 3. The least significant bit should go out first. So here is the code for it. We have unsigned character current byte equals to 0x44, and then unsigned character reg ALS SB, unsigned character X, and then a regular. We are giving the regular ALSB character equals to count byte, which means regular ASB reg ALSB has value 0x44. Then DDRC or equals to 1, and serial pin here you can define as value 3, so which means the third bit is being third bit of port C is being set to 1. Then we have a for loop here which will run 8 times, but we have 8 bits of the hexadecimal value 44. And then we have the if condition that if 0x44 and 0x01, which means that if this will be so here when we are performing AND operation, we know that when AND is performed with 1, that is results in 1, and when with 0 it will have no change. So only the first bit we can see 0x01, which means only the first bit will remain unchanged, and other will be changed to 0, as AND's operation is that where when anything is ended with 1 there will be no change, anything ended with 0 will become 0. So port C's we are sending this. So here now we will be sending port C. At port C pin 3 will be given high, and else if this is not the case, then the third pin of port C will be assigned the value 0, and we will shift the EGALSB one position to the left, which is now it will be taking the second bit. And similarly this loop will continue until all the 8 bits are sent to the third pin of port C. Now here we are writing a C program to send out the value 44 serially 1 bit at a time via port, and now this time most significant bit should go first. So similarly everything will remain same. The only change here will be that when will be here will be that when we are the if condition, the regular ALSB has the 0x44 value, and it will be ended with, instead of the first we ended it with 0x01, so instead of this we will be ended it with 0x80, which means the 8th bit is 1 and all the other bits are 0. So if the 8th bit is 1, then port C's third pin will display will give high, and else it will give low, and this time the shifting will be towards the right side, and regular REG ALSB will shift towards the right side after every cycle. So now example 34, we are C program to bring in a byte data serial 1 bit at a time via port C. Pin 3, the least significant bit should come in first, so character X, and then a character reg A equals to 0, and then we are setting the port C's third pin at not 1, which means 0, so an input direction. Then there's a again for loop, and then we're shifting 1 bit right, and then storing that we are copying basically, or storing, we can say that the third if there's a 1 at the third port of pin C, so we'll set it to 1 and copy it to 7th of the serial pin, so 7 minus serial pin. So here our third pin will be set to 1, and our 7th pin will be also set to 1, which will be the most significant bit. Now we are writing a C program to bring in a byte of data serially 1 bit at a time via port C pin 3, and my most significant bit should come first. So again the code will remain same. The only change that will be here is that our shifting that will be taking place towards the left, and when we'll be copying from port third, we'll be taking input from the third pin of port C with pin C and 1 less than serial pin, and then we'll be copying it to the serial pin, which is the third pin, and this will be the least significant bit of REGA. So now moving on to chapter 9, which is Avr Delay Timers. So here in this example we'll be looking at the program written in C language to toggle all bits of port B continuously with some delay, and we'll use timer 0 at normal mode and with no prescaler options given to it. So first we can see we have the input output header file, and then the int main function, and before int main we have declared a prototype of the function t0 delay, and then here after int main we can see we have defined that function. So we have void t0 delay, and in it first line we can see tc and t0 equals to 0x20, which means that we are writing the value to hexadecimal value 20 in our timer 0, and so which means that our the counter will basically start from 0x20 till 0xff, and then we have to set it for timer 0 in normal mode and no prescaling. So for that we have to make the combination of our TCC R0A and TCC R0B and set it to a combination of 001 of the D bits. So that's why sending TCC R0A to 0 and TCC R0B will give us that combination, for which we will be able to run it on timer 0 normal mode without prescaling. And then we can see the while loop, which has a condition to check the T0V flag, which is the overflow TOV0 flag, which is the timer overflow flag. So the timer overflow will occur when the TCNT value reaches 255. So the TOV overflow flag will become 1, so which means that this loop will start from 0x20 and continue till the T overflow becomes 1, or the TCNT or the TIFR is equals to 1. So this is that many times the while loop will run, and after that as the loop will end, so these many cycles will be wasted and a delay will occur, and then TCCR0 is be equals to 0, which means that we have set the TCCRE0 from removed it from normal mode and no pre-scaling, and we have basically turned it off, and we have cleared the overflow bit in the last line. And then when coming to int main, we have set the port B direction to all pins output, and then we create a while loop in which we are displaying first the setting the output at port B 0x55, and then we are causing this delay, which will start from 0x20 till and go to 0xFF. 0x20 is basically in a decimal, we can say it makes the value 32. So from 32 till 255 we are going these many cycles, wasting these many cycles to create a delay, and then port B will change the output 0xAA and then again a delay, and this will keep happening. Now example 40, here we are in C program to toggle only port B of only fourth bit of port B continuously every 35 microsecond, and again in timer 0 using timer 0 normal mode, and this time we'll be using pre-scaling 1/8, and assuming that the crystal is 16 megahertz. So first of all we have created here the find the period of the machine cycle, which is 1/16 frequency, which is 16 megahertz. Then we'll be converting this frequency with the pre-scaling this time period. So we'll just multiply it by the pre-scaler, which is 8, and which will give us 0.5 microsecond delay. So to have a 35 microsecond delay, we'll simply divide it by 0.5 microsecond. We know that we'll need to have 70 clocks to get this delay. So if we do the counter starts from 0 to and goes to 255 until the TOV flag is 1. So we need to increment the counter 70 times. So basically we will subtract the 70 from the 255, and the value that we will have, which is 186, we will load this in the TCNT 0 register, so that it can start the counting from this value 186 and will go to 255. So input output header file is there, function T0 delay. There in the function we can see we have loaded the counter with value 186 and set the combination of TCCR0A and B to 0 1 0 for the D bits, so that we can operate it in normal mode with the pre-scaling of 8. And here is our while loop condition, which will look for the timer overflow flag, and the counter will start from 186 and go till 255, and then the TOV will be equals to 1. So then at that time this while condition will become false, and then a delay will end, or a loop will end, and then we will be simply turning off the timer and clearing the T overflow flag. And then in the int main we can see we have set the port B again output direction, create a delay, called the delay, and then toggle only port be 4-bit continuously every 1 millisecond using timer 1 normal mode and no prescaler. So only difference is here that we are just changing the number of the time that we used for delay, and we are using, this time we are using timer 1 instead of timer 0. So again all the steps will be the same, but this time will be resulting in a different number of clocks that we need. So we will be starting from here. We can see we have got the time period here 0.60625 microsecond, and we have no prescaling, so it will remain the same for the clock. Machine cycle will be the time period of machine cycle will be the time period of the clock, and then 1 millisecond will be divided by 0.0625 microsecond. We will need 16,000 clocks, so we'll write that in hexadecimal. Just we will add 1, so because of for that 55th cycle, and the next one cycle to raise the time overflow flag. So we have the hexadecimal value 0xC180. So again let's go to the timer 1 delay function first, and here we have we have load the values C180 in two different timer counter registers. So then we have used the TCCR1 and A and B to set it to normal mode and no prescaling, and then we'll create a while loop to check the timer overflow of 1 is equals to 0 or not, and when it will first start from this 80, and then C1 it will go from 80 to 255, and then it will be cleared, and then C1, and then it will start from C1 and again go to 255, and so this will give us 16,000 clocks. And then we have just turned off the timer, and by cleared the timer overflow bit. Okay, so now here we have just the only differences in this code that we are just pre-scaling it with 1024, and our clock cycle has also changed from 1 millisecond to 1 second. So again everything remains same, only the change will be that when we will be assigning values to our TCCR1 A and B, these will change according to the combination that we need for the 1024 pre-scaling, and the number of clocks we need for to create a 1 second delay, that will also change. Because in the previous example there was no pre-scaling, but this time there is, so we'll just multiply our machine cycle with the pre-scaler and then find out the number of clocks we need, and then all the other operations are just same. Okay, now assuming that a 1 Hz clock pulse is fed into pin T0, use the TOV0 flag to extend timer 0 to a 16-bit counter and display the counter on port C and port D. So first of all, again you can see there is the input header output header file int main, and then in the int main specific number of delay, time of delay to create. Then there's a while loop and while do loop, and in here we can see that port C. At port C we are entering the we are giving the value 0, which is basically from where our counter will start, and this will continue to happen until the overflow flags becomes 1. So as this becomes 1, our output will basically show, port C will show us the continuous value of t counter, which will from 0 then go to 1, then 2, then 3, then 4. It will continue to go till 255, and at that time so basically port C will be showing all the values from 0 till 255, and then this loop will exit, and then we will clear the timer overflow bit, and set the value of port. We increment the value at the port B. So this is that time we will know that that our cycle has ended. Now example 44. Assume 1 Hz external clock is being fed into pin T1. Write to C program counter 1 in rising edge mode and to count pulses and display the. Okay, so this time we are using timer 1, and again we have an external clock, and we will be using the rising edge mode, not the normal mode. So and we will be displaying the T counter 1 H and T counter 1 L, which means basically the number of clocks on the output ports B and C. So here we can see in the int main we have set we have given a pull up to port D of and then we have set the port C output direction, port B output direction, and then TCC R1 A and B combination is set according to make it work on rising edge, and T counter 1 equals to 0, and in the while loop we can see that port C will display the T counter 1 L register value, and port B will show the value of T counter 1 H register value, and this will continue to happen until the value goes from 0 to 255, and at that time the flag will be raised, and then the flag is cleared, and this loop will repeat forever. So these are all the examples from this chapter. So here we have completed our assignment, and we have looked at all the C language codes for AVR programming and AVR timers. Thank you.